Hello folks, welcome to the second part of Defect Chemistry of Ceramics course. In the first lecture, you learned what are defects and the classification of defects and then thermodynamic stability of defects. In this lecture, you will learn the possible point defects of pure stoichiometric compound MX, and then we will apply this basic knowledge to establish the defect structure of a pure stoichiometric compound. So these two topics will be your job today. Okay. Let's discuss the ionic point defects of pure stoichiometric compound MX first. First of all, let us ask, what is a stoichiometric compound? Probably you may have heard quite often stoichiometric compound or stoichiometric coefficient and so on. Stoichiometric compound means that, for example, for the case of sodium chloride, the number of cations or concentration of cations and the concentration of anions are exactly equal to each other. For the case of sodium chloride, it should be 1:1, okay? No other possibility. This is the definition of a stoichiometric compound. So composition is fixed. You see, sodium 1 and chlorine 1. But actual crystals, well, does not necessarily satisfy this stoichiometric condition. Depending on thermodynamic variables of your system, the M to X concentration ratio is quite often off 1. So that deviation from the stoichiometric ratio is normally represented by delta. And this delta is called, so to say, non-stoichiometry or deviation from non-stoichiometric compound. Okay? So in this lecture, we assume that this delta is negligibly small compared to 1. Therefore, our compound is assumed to be, so to say, ideal stoichiometric compound. Okay? Okay, for this kind of stoichiometric compound, what kind of point defects are possible? Let's catalog them. Okay? Now, for the case of MX or NaCl, we have two sublattices, cation sublattice and anion sublattice. So each sublattice has its own point defects, and then misplaced ions, will take place. Okay, you see, missing cation. In ideal structure, this cation site should be charged with positive unit charge, okay? Sodium +1. There, you put the emptiness, namely vacancy, which has no charge at all. So we represent this point defect in this way. We normally express the site of defect as the subscript, and then species, on the normal place, and then the actual charge of this species is normally written as the superscript. Okay. Okay. The second defect, which is possible, is the interstitial cation on interstitial site. This cation is singly charged. Its location, namely its site, is interstitial site, so whose charge is just 0. Okay? And then misplaced cation, namely cation sitting on anion site. Anion site should have the negative unit charge for the case of NaCl, and the cation sitting on the anion site is charged with a +1. Okay. Now what about the anion sublattice? Okay, vacancy on the anion side. Now pay attention to the actual charge notation. Here, site has the -1, charge of -1, and vacancy has 0 charge because vacancy is nothing. And then interstitial anion, okay? Monovalent anion is sitting on the neutral interstitial site. So again, I would like to draw your attention to the representation of actual charge. This actual charge corresponds to this species sitting on this site. And here, this 0 represents the actual charge of interstitial site. Then misplaced anion. Okay, now anion with minus charge -1 sitting on the cation side with actual charge +1. Okay, and here is the a bit confusing, concept or language. That is the effective charge of a defect. Now, let's try to understand effective charge and actual charge first. Actually, this kind of charge is actual charge. Here, I represented them in numbers. Okay, here is the ideal crystal. So, for example, for the case of sodium chloride, you have the you have the pattern of distribution like this: plus, minus, and in this direction, all plus, minus. So, plus and minus occurs alternatively. Okay, so each ion, for example, negative ion here, tries to have as many possible cations in its nearest neighborhood. Likewise, positive charges also like to have the negative charges, in the nearest neighbor. Okay, this is the ideal crystal structure. Okay, now let's take this repeating unit, which we call unit cell. Okay, now here you have the positive charges at the 4 corners, and then 1 positive charge at the center. How many positive charge units does this unit cell have? Here is the answer. Now, each ion has the charge of +1. Then this ion makes a contribution of a quarter to this unit cell, right? So 1/4. And there are 4 of those. And then right at the center, we have the 1 ion as a whole within this unit cell. And what about negative charge? Yes, at the each edge we have the 1 negative charge. So you see 1, 2, 3, 4, and the edge ion makes a contribution of 1/2 to the unit cell. So you see each ion has the -1 unit charge, and each makes a contribution of 1/2, and we have 4 those in total. So what? This makes the 0. So this means this repeating unit has the is just electrically neutral, because it's quite simple, and each repeating unit should have the no net charge at all. If it had any real charge, then they repel or attract each other, to distort whole structure. So this kind of principle is called local charge neutrality principle. What about this, unit cell, which is the smallest possible repeating unit? Again, same idea can be applied to this unit cell. I would like you to follow, this calculation here to see this unit cell has 0 net charge. Okay, so far so good. Very simple. Now suppose that we take off 1 positive charge, which used to be here, to make 1 cation vacancy. This is cation vacancy, okay? This species here. Let's count how many charge units does this unit cell have? Now you see, we have a vacancy which has the 0 unit charge sitting on the cation side with actual charge of +1. Don't forget this notation, okay? Now there are 1, 2, 3, 4 cations, right? And each one makes a contribution to this unit cell 1/4. So total positive charge is just 1 here, right? 1, 2, 3, 4. And each makes 1/4 contribution to make the actual charge contribution to this unit cell just a +1. What about the negative charge? Oh, we have 4 negative charges here, here, and here. Each makes a contribution of a half. So this makes the -2 unit charge contribution. What about the net charge then of this unit cell, involving the cation vacancy? Yes, it it is as if it has the -1 unit charge here. This so to say defect entity. Okay. This -1 turns out to be equal to 0 minus this charge, namely the actual charge of species sitting on this side minus actual charge which there should be on that side if ideal crystal. So 0 minus 1 makes, you see, -1. Oh. So we would like to distinguish this actual charge from the discharge. This is the actually effective charge of this repeating unit. So we call this one effective charge. And I would like to represent this effective charge as, say, single prime. If it were of 2 units, then it would have 2 primes and so on. Okay? Oh, sorry. Okay, what about the anion vacancy? This is very amusing. Here is the anion vacancy. There used to be 1 negative ion here. What about the effective charge of this repeating unit? We have 4 negative charges at each corner, which makes a contribution of 1/4 each. So it makes a -1. And what about the positive charge? You see, 1, 2, 3, 4 at each edge, which makes a contribution of a half each, to this unit cell. So the total charge turns out to be +1. When you have the missing negative ion, this repeating unit turns out to have the effectively +1 charge. This +1 turns out to be equal to the actual charge of this vacancy minus the actual charge of this side if our crystal is ideal. So this effective charge or positive effective charge will be denoted by dot, or if doubly charged, then we put 2 dots and so on. So this is very important concept in defect chemistry. So you have to be able to distinguish actual charge and effective charge. Okay. So let me redefine the effective charge once again. Effective charge is here actual charge of a species sitting at a site, okay, minus actual charge there in ideal crystal. Okay, let me take a few examples. This is the really straightforward example. Let's say sodium ion sitting on sodium side. Sodium has the actual charge of +1, right? And each side should have the also +1 charge. So actual charge of this species minus actual charge here, okay, is side, makes 0. Therefore, effective charge is 0. So effective charge 0 is normally represented as just x. Okay? So we say we represent normal sodium on sodium side as just x. What about the chlorine ion on chlorine side, chlorine ion side? Okay? This has the minus charge 1, minus 1, and this side has minus 1 as charge. So it makes 0. So we represent this one in terms of effective charge, say x. What about the sodium vacancy? We just analyzed in the previous slide. This vacancy has 0 actual charge, and this side has positive unit charge. So this charge minus the charge there makes -1. Therefore, its effective charge is -1. So it is represented by prime. What about the chlorine ion vacancy? Likewise, you'll see it turns out to have the effective charge of positive, +1, because this vacancy has 0 charge and the chlorine ion has -1 charge. Therefore, 0 minus -1 makes +1, right? Okay, now final example. Let's skip the sodium interstitial. Chlorine ion on the interstitial side. What about its effective charge? Okay, chlorine ion, its actual charge is -1. But interstitial site itself should have no charge if your crystal is ideal. Then this difference makes -1. Therefore, effective charge of chlorine ion on the interstitial side, makes the effectively singly charged. So it is written, it is represented as like this. Get it? Okay, so now let me introduce you the very important, so say, notation of defect, which is actually invented by Krog and Vink in the Philips Research Institute in Netherlands. So it is called a Krog-Vink system of notation. It goes like this. So you represent you write a species, on the normal line, and as the subscript, you put the symbol for the specific location, okay, locus or site within the lattice, and then you put the charge state on the, as the superscript, okay. This charge can be represented either in terms of actual charges or in terms of effective charges. Now, as you see here, let me take the sodium on sodium side. If we represent its charge state in terms of actual charge, then we have to write, say, 1 plus and 1 plus in this way. It's too complicated, right? But in Krog-Vink system of notation, it is written simply as sodium on sodium side with 0 effective charge. How beautiful it is. This is very important in defect chemistry. You should understand this Krog-Vink system of notation, which consists of 3 things. Number 1, the major entity, which represents the species you are now trying to describe. And then as a subscript, always you have to put the symbol for the locus or site. And then as the superscript, you have to put the charge, okay, in terms of effective charge. Very important. But it's quite simple, right? And I would like to emphasize the definition of effective charge here. Effective charge is actual charge of a species, this one, minus actual charge there, here, in this location. Okay, they're in ideal crystal. Okay, then what kind of defects are possible in the stoichiometric, pure stoichiometric compound, MX? I mean by pure, it's really pure. You know what I mean, right? Pure. No impurities at all. Only M and X. And the stoichiometric means just M1 and X1. Okay, let's construct this ideal crystal first. Let's say sodium chloride, okay? Then you see, you have to put the sodium on sodium side and the chlorine on chlorine side and the vacancy on interstellar side, because the interstellar sides are supposed to be all vacant. Now you have these three species, sodium and the chlorine and the vacancy, okay? Then we put the sodium on sodium side, this red stuff. Chlorine on chlorine side, so negative ion on negative side, yes? And the vacancy on interstellar side. Oh, sorry, I made a mistake. You see, sodium on sodium side, which has the neutral charge. Chlorine on chlorine side, neutral. And the vacancy on interstellar side has the neutral charge, effectively. So once you are given these three things, namely three structure elements, you can construct ideal crystal sodium chloride. So in that sense, these three species are called regular structure element. Regular structure. So by distributing the regular structure element in the lattice, you end up with the ideal crystal sodium chloride. Okay? What about the real crystal? Real crystal means a crystal containing defect. For example, you see vacancy here and the interstitial here and so on. Okay? Okay, we have the sodium side and the chlorine side, namely negative ion side, and the interstitial side for this case. We have the three species again, okay? Sodium ion and chlorine ion and vacancy. Okay? Its effective charge, don't forget, yes, its effective charge is +1, chlorine ion -1, vacancy 0, actual charge. Oh, sorry, actual charge. Okay. Okay, now we have the three regular structure elements. And then real crystal should have the defect. That's why we call it real crystal or actual crystal, due to the, because of the, the entropy effect. So that's why these point defects are thermodynamically stable, which often is referred to as the defect of entropy origin, okay, or thermal disorder. Now, let's introduce the defect. Missing cation, okay, effectively negatively charged. Missing anion, interstellar sodium ion, interstellar chlorine ion. Now, misplaced cation, misplaced anion. Now you can understand why these species have the, just a single prime or single dot. It's clear, right? But here, misplaced cation, namely sodium on chlorine side. Why does it have the effective charge of +2? You see, sodium has the actual charge of +1. Chlorine side has the -1, okay? Therefore, it should have the effective charge of 2 units. Likewise, chlorine on sodium side, this misplaced anion should have the effective charge of -2. So that's why it should have the 2 primes. So this kind of point defects are quite often referred to as irregular structure element, which are nothing but the point defects. So by distributing these structure element, you can construct an actual crystal, this one. Vacancy, interstitial, misplaced cation, misplaced anion, and so on. This is actual crystal, okay? Okay, then finally, let's try to analyze the ionic point defects of pure stoichiometric compound MX. We have to understand how these defects can be generated. there are two conditions obeyed always. For example, you see, let's take another example, alumina, okay? Al2O3. Now, in this structure, aluminum side, cation side, and the oxygen anion side, their ratio should be 2 to 3. You see, there are aluminum 2 and oxygen 3. So alumina structure has the cation side and anion side, whose ratio should be 2 to 3. Otherwise, it cannot make the alumina structure itself. Okay, now whenever you like to generate a defect, you have to satisfy the structure condition. This condition first. Okay, now suppose that you have a variation of cation side by introducing vacancy or misplaced anion or whatsoever. Okay? Then this variation of cation side should be equal to 2/3 of the variation of anion side to satisfy this structure condition. This is the utmost important condition which has to be satisfied upon the generation of defect. Without satisfying this structure condition, then your host lattice is no longer alumina, because this structure condition is just disobeyed. And the next condition which should be satisfied upon generation of defect is the charge neutrality condition. Yes. Any variation of positive charge should be compensated by the variation of negative charge. Okay? So in this sense, always, defect can be generated in pair. I mean by pair, say positive charge defect and a negatively charged defect pair. So how many different kinds of defect pairs possible? Okay, positive charges, let me write down, on this row. Okay, missing anion, interstitial cation, and misplaced cation. Pay attention to the number of effective charges. Now, a negative species is missing cation, interstitial anion, and misplaced anion. Again, be careful with respect to the number of primes. Now it's quite obvious to imagine that this pair is possible because one has the positive charge and the other one is negative charge. So all these pairs are possible. So ideally, 9 kinds of the defect pairs are possible. Namely, these defect pairs can be generated simultaneously satisfying the structure condition as well as the charge neutrality condition. How are they generated? Okay, let's just write down the generation reaction equation. What you have to be careful about are those two necessary conditions to be satisfied. Number 1, structure condition. Number two, charge neutrality condition. Okay? Okay, here. Now ideal crystal is here. M cation sitting on the cation side and anion on the anion side. Okay? You see, now this N cation moves to the surface, leaving behind a cation vacancy, and X anion moves to the surface, leaving behind a anion vacancy with the effective charge of +1. You see, now on the surface, this M and X makes another social molecule. We call it lattice molecule in defect chemistry. Okay, lattice molecule can be somehow distinguished from the normal molecule. So we call it lattice molecule, okay? Now, if you remove the, this M and X from both sides, because mass is conserved, then left-hand side turns out to be 0. So in European literature, or in the older literature on defect chemistry, they used to use nil instead of 0. So from nil, cation vacancy and anion vacancy, both defect pair can be generated. Okay? Now check whether structure condition is satisfied. Yes, anion site, one anion site and one cation site defect are generated. So site ratio is 1:1 because our lattice is 1:1 lattice. What about charge conservation? Yes, left-hand side, actual, the charge is 0. And on the right-hand side, charge is 0. Therefore, charge conservation is satisfied. Okay? Like, similarly to the normal chemical reaction equation, the actually third condition should be satisfied, mass conservation. It's quite obvious. So normally we have to, check the number 1, the site conservation, and the number 2, charge conservation, and the mass conservation. What about this pair? Okay, here is the normal cation and normal X ion. That's why they have the effective charge of 0. This is a regular, ideal crystal. Okay, let's suppose that these two guys go to the interstitial site to make the positive, effectively positively charged cation, interstitial cation, and the effectively negatively charged the anion. And then you see this vacant site leaving behind and anion vacant site to make a kind of lattice molecular vacancy. This disappears. Okay, another defect is, let's say regular M goes to the interstitial site, okay, likewise. So you can actually write down by considering these 3 conditions. Let me leave these defect generation equations just for as exercise for your fun. Okay, possible defect types for MX now is, so as I told you earlier, this type is possible, this is possible, this is possible, and everything is possible. But this one and this one, actually energetically too expensive because it involves too many defects. So energetically possible defects are normally these 4 kinds. So this number 1 type is called Schottky disorder, okay, vacancy pair. And number 2, this is the interstitial pair, which is called anti-Schottky. Anti means, the opposite, right? And then number 3, this is the cation interstitial and the cation vacancy. That makes Frankel disorder. And what about 4? This is the mirror image of this Frankel disorder concerning the anion sublattice, so which is called anti-Frankel disorder. And what about this 5th defect? Actually, this 5th kind is energetically, as far as myself is concerned, I never seen it. But anyhow, it has this special name because M goes to the X side and X goes, come to the M side. So structure is quite opposite. Therefore, it is called anti-structure disorder. Okay. Okay, then pure stoichiometric, the defect structure of pure stoichiometric compound MX is quite simple. Well, let me tell you its logic. For this system, it is possible to have it depends on the crystal structure of your compound. Okay? Suppose that this system have the Schottky defect. Then defect formation reaction is written in this way. And then it needs some work you have to do to create this defect pair. So this is called defect formation gives free energy. In this case, Schottky disorder, therefore we put S here. Okay? So by eliminating the M and X from both sides, you end up with this kind of defect formation reaction. And then how to calculate the equilibrium defect concentration is quite easy. You can simply apply the mass action law. Okay. Now suppose that you create M plus cation vacancy and M minus X vacancy, okay, out of the large N cation side and the large N anion side. Then you can simply apply mass action law to write this kind of, say, concentration ratio. This gets you the kind of equilibrium constant, namely Schottky defect formation equilibrium constant. Okay, now I'm recollecting your knowledge of the chemical equilibrium. You can write this equilibrium constant in this way, in terms of the Schottky defect formation gives free energy. So in defect chemistry literature, you normally write this mass action law in this way. So the fraction of cation vacancy times fraction of anion vacancy. So this corresponds to the anion fraction, vacancy fraction. This corresponds to the cation vacancy fraction. So we normally write in this way. Okay. Okay. Now, very simple story about pure stoichiometric compound defect structure. Okay. Okay, so this is the Frankel defect formation case. Now you can apply mass action law, as before, to write down in this way. So this is called Frankel defect formation equilibrium constant. In defect chemistry jargon, you write in this way. And misplaced, say, anti-structure disorder or defect, again, by applying mass action law, you can write the anti-structure equilibrium constant in terms of the anti-structure defect formation gives free energy this way. Okay? Okay, so finally, you see, let me emphasize again. In writing down the defect formation reaction, you should not forget the three constraints, which have to be each satisfied, namely side ratio conservation or structure condition. Okay, this one, side ratio. And then charge conservation, here, charge. And then mass conservation. Now you can recognize the beauty of the, Krog-Bink system of notation. Three things and three conservation constraints. Okay, don't forget. Okay, so this should be, I would like to make this one my last slide. Here is the example of defect formation energies. Okay? For example, say silver chloride, which has the Frankel defect, whose formation enthalpy is about 1.1 eV. And for example, another system, zirconia, you see oxygen, say Frankel, namely anti-Frankel disorder, and normal Frankel disorder, cation Frankel, and Schottky disorder. Now you can see the how expensive their formation energies are. Here, rule of thumbs, which I would like to tell you. Number one, when there are many possibilities of defect pairs, normally the energetically cheapest one is the majority disorder type. For example, for the case of zirconia, you see the cheapest one is anion, say Frankel, namely anti-Frankel disorder. Okay? If the structure is closed, like a face-centered cubic or something like that, then Schottky disorder is normally the majority disorder type. And the open structure like the Urscheid structure or and so on, or the PCC structure, then Frankel disorder makes the majority disorder type. Okay? So these are the actually rule of thumbs. And as you can see here, defect formation enthalpies has a wide spectrum. So whenever you are given this list of defect formation energies, then try to look for the most, actually the cheapest one energetically. Okay? Okay, so let me finish our second lecture here, and we will continue the next story in the lecture number 3. Okay, thank you so much, and we will see in next lecture. Okay, bye-bye now.